Hello everyone, welcome to ML Summer School. I am Anshuman Maurya, an applied scientist on Central Machine Learning team. Welcome to the Deep Learning Fundamentals module. Over this module, we are going to build up the foundation of deep learning from the ground up. You will learn how a neural network is built, how it learns to make a prediction, how we train it to actually work well. This part is about architecture, why deep learning changed the field, and how we went from single neuron all the way to a multi-layer network with activation functions, right? So yeah, so let's dive in. Deep learning fundamentals. Uh, to appreciate the deep learning was such a big deal, we have to understand what came before it, right? So about 50 years, artificial intelligence meant humans hand engineering what a model should look for. If you wanted to do a computer vision, it personally designed feature detectors like edge detectors, corner detectors, things called SIFT and HOG. For language, you hand-built parse trees and grammar rules. This took months of expert work for every single task, and this is painful part, right? None of it got transferred. The features you designed for detecting cats were useless for detecting cars. You started from scratch every time. Then in 2012, one neural network changed everything. The idea was radical. Instead of telling the model what features to look for, you feed it raw pixels or raw text or raw video, and the network learns the feature itself. And the same basic recipe work across every domain: vision, language, speech, and code, right? Um, so here are the numbers that made everyone pay attention, right? So on ImageNet, the big image recognition benchmark, the error rate dropped from 26% to 16%, basically overnight, right? By 2015, deep neural networks were beating human level performance around 5%. Today, it's nearly 3%. The verdict was final. When you have enough data, learned features beat hand designed features every time. That's the shift this whole field is built on. Um, so why does simply stacking layers learn such a good features, right? The key insight is that deep neural network isn't one giant classifier, right? It's a pipeline of feature detectors where each layer builds on the one before it. So if you look from left to right, the network takes in raw pixel. The first layer learns to detect simple edges. The second layer combines edges into textures. The third layer combines textures into object parts, an ear, an eye, a whisker. And the final layer combines those parts into a whole object and says that's a cat. The crucial thing is nobody programmed ear or whisker, right? Those detectors emerged automatically from the data. So this isn't just vision. In language, the early layers learns characters, the word pieces, deeper layer learns grammar, and the deepest layers capture the meaning. It's the same principle everywhere, right? Stack simple, learn transformations, and raw data turns into understanding. Now let's build this up from the smallest possible piece, a neuron. So the one, the perceptron, why it famously failed and how stacking neurons fixed it, right? So the simplest neural network is a single neuron called perceptron from way back in 1958. It does three things. It takes each input, multiplies it by a weight, that's how much that input matters. It adds up those weighted inputs plus a bias, which is just a tunable threshold. And then it applies a step function. If the total is positive, output 1, otherwise output 0. Learning just means adjusting those weights and biases until the decision boundary sits in the right place. And notice in the code, the perceptron is literally one linear layer followed by a threshold. But here's the catch, uh, and it's famous one. A single perceptron can only draw one straight line, right, through an input space. It can learn simple logic like AND and OR, but it cannot learn XOR. It's because no single straight line separates the XOR case. Minsky and Peppard proved that this in 1969, and the disappointment set off what people call the first AI winter. The fix decades later was almost embarrassingly similar. Stack the neurons. That's the next slide. Let's go on to it. So here's the problem, stated clearly, right? XOR is not linearly separable. One straight line can't split the two classes. So a single neuron is stuck no matter how long you train it. The solution is a multi-layer perceptron. Uh, you wire many neurons into layers, an input layer, one for hidden layers uh, in the middle, and an output layer with a nonlinear activation between them. Each hidden neuron learns its own boundary, and by stacking them, the network can bend and fold the input space until the classes finally become separable. So look at the diagram. Three inputs, two hidden layers for four neurons, two outputs, and every single row is a weight the network learns, right? This is a multi-layer perceptron. So what actually does a layer computes, right? Little precise about yeah, it does three things in order. It multiplies the input vector by a weight matrix W. It adds a bias vector B, and then it applies a nonlinear activation sigma to each element. That's the question, right? H equals that's the equation, right? So H equals sigma Wx plus B. Now look at the matrix. W has one row per output neuron, and each row holds the weights connecting every input to that neuron. So you can read each row as one neuron's feature detector. The important practical point is because the whole layer is a single matrix multiply, it maps perfectly onto GPU hardware, which is built to do exactly this, right? Massive parallel matrix multiplication. So that's a big reason deep learning became practical at all, right? And one thing to hold on to, because this drives the whole next chapter, without those activations, the ReLUs in the code, right? The three linear layers would just collapse into a single matrix. Depth would buy nothing, right? So so let's do a quick check, right? So suppose you stack three linear layers with no activation between them, right? What have you actually built? You can take a second uh, and maybe think about it. Right, so the answer is B, right? So without nonlinearity, W3, W2, W1 is just another single matrix, right? The composition of linear functions is linear, right? So you have spent extra parameters with gained zero extra representational power. This exactly by activations are what make depth meaningful, which is our next topic. So just saw activations are essential. So now which activations do we use and why, right? So let's make it concrete. Um, an activation is just small nonlinear function applied to every neuron's output right after the matrix multiply. It looks like a minor detail, but without it, depth is an illusion. So here's the problem side, right? Uh, Stack of linear layer and collapses into one, right? As we saw in the previous example, W3, W2, W1 is just another matrix. So so a 100-layer linear network has exactly the same power as a single layer, right? It can only ever draw straight boundaries, no XOR, no curves, no vision, no language, right? So the solution is to insert a nonlinear function after each layer. Now the layers no longer collapse and each one bends the feature space a little, right? Stack enough to those bands and the new network will carve out arbitrarily complex shapes. That's what makes the deep neural network a universal function approximator. Um, so the question is, what makes good activation, right? Four things. It should be a nonlinear, so depth adds power. Its gradient shouldn't vanish, so deep layer keep learning. It should be cheap to compute, so it runs on every neuron, every step, and it should help training coverage fast and stay stable. So we'll judge every activation against three these four criteria. Um, so sigmoid and tanh, let's start with the classic ones, right? The smooth S-shaped squashing functions that were the standard for decades. Understanding why they fell out of favor motivates everything after, right? So sigmoid squashes any input into a range of 0 to 1. So its output reads nicely as a probability, but its gradient peaks at only 0, 0.5. And it's basically flat for large inputs. Multiply that tiny gradient across many layers during training and it vanishes. So the early layers stop training. That is a fatal flaw. 10H is better. It squashes into -1 to 1 and it's zero centered, which makes gradients behave better and its gradient reaches at the center, right? Reaches 1 at the center. But it still saturates for inputs beyond about 2, right? So deep 10H networks still suffer from the same vanishing gradient problem. The takeaway is the warning at the bottom, right? Never use sigmoid or 10H in the hidden layers of a network. Their gradients vanish. They survive only in the specific spots. Sigmoid on a binary output or a gate, 10H inside a RNN cell. For hidden layers, we need something that doesn't saturate, right? That's the that's the next activation. Um, so these three are what actually you will use, right? ReLU is a workhouse. It passes positive values straight through and clamps negatives to 0. That one simple rule fixes most sigmoids problems. For positive inputs, the gradient is exactly 1. So the signal flows through deep stacks without shrinking. It's sparse, it's trivially cheap, and it's converged about 6 times faster than the sigmoid in that 2012 results that kicked off the boom. ReLU has one failure mode, right? Which is called dying ReLU. If a neuron input is always negative, its gradient is 0 forever, and it's effectively dead. The fix is leaky ReLU, right? Which gives negatives a small slope so that little gradient always survives. So you see it in the second plot, right? The line dips gently below the axis instead of going flat, right? Uh, Gelu is smooth version of ReLU, no hard link, and it's the default for transformers like BERT, GPT and Llama. And softmax is different from others. Its output activation, it turns a vector of raw scores into a proper probability distribution that sums to 1. Rather than reading the whole table, here's the rule to remember, right? Is the last column. ReLU for the hidden layers of CNNs and MLPs, GeLU for the transformers, um, sigmoid only for the binary output, softmax on multi-class outputs, right? So here's a quick concept check again. So yeah, so please go through this and let's think about it. What is the right answer here? Right, so the answer is B, right? Um, yeah, so software is applied twice, right? Cross entropy loss already applies log softmax internally for numerical stability, right? So passing pre-softmax values squashes the output toward uniform and shrinks the gradients. Um, so the rule is basically always pass raw logics to cross entropy loss function, right? Never softmax probabilities. So basically, yeah, so this is end of the part one. Right? Deep neural networks win because they learn their own features in a hierarchy straight from the data. We built one from a single perceptron to a multi-layer network where each layer is a matrix, multiply plus plus a bias, right? And we saw that nonlinear activations are what make depth meaningful, with ReLU and GeLU being the modern defaults. In the next part, we will see how data actually flows through this network and to produce a prediction, right? And how network learns from these mistakes. So now how does the data actually flow through the network, right? To produce any output, right? Um, so here's the problem. We have a input X, a set of learned weights and a biases for every layer. So how do we turn them into an actual prediction, right? The answer is forward propagation, and it's simpler than it sounds. You push the input through the layers one at a time in order, and each layer's output becomes the next layer's input, right? Every step is the same recipe, a matrix multiply and then a nonlinear activation. So let me walk you through the pipeline. Um, we start with the input X. The first linear step Z equals to WX plus B. Then an activation ReLU. Another step, uh, right, which is again a linear combination of the previous activations, right? And then we apply a softmax, right, to give out the class probabilities. And finally, the next is the loss, right? Which scores the prediction against the ground truth, right? The thing to notice is inference stops at the prediction, right? Training continues one step further into the loss because that's what let us connect the correct network, right? So let us, I mean, take an example and see how it works, right? So so layer one, right? It's a hidden layer. We multiply by the weights and add the bias to get the pre-activation Z1, right? Um, Now, once we get that, we apply ReLU to the Z1s and we get the activations, right? The layer two, the output layer, basically we feed those hidden activations from the previous layer. The weighted sum comes to around 0.8, right? And the sigmoid squashes that into a 0.69. Okay. So the model is 69% confident the label is 1, right? Um, Now we come to the loss, right? We compare 0.69 to the true label using cross entropy and get the 0.371. Um, uh, right? So sigmoid is cautious, like that single number is uh, how wrong we are. Hold on to it, right? We are about to reduce it. Um, right. So let's actually trace one all the way through the real numbers. So it's not this abstract tiny two-layer network. Let's go through it. Right. So the layer one, right? We multiply by the weights and add the bias, right, to get the pre-activation Z1. Then ReLU clips the negative value minus 0.1 up to 0 and lets the positive value 1 pass through unchanged. The layer 2, the output, we feed those hidden activations in. The weighted sum comes to 0.8 and sigmoid squashes that into 0.69. So the model is 69% confident that the label is 1. And the loss, right? So we compare 0.69 to the true label using cross entropy and get 0.371, right? That single number is how wrong we are. Hold on to it. So we are about to reduce it. Um, so one more thing happens during forward pass that you don't see. As it runs the framework, the PyTorch here, right, silently records a graph of every operation, a directed cyclic graph, uh, a directed acyclic graph, and each node remembers its input, right? In practice, you never build this by hand. You just call model of X as in the code. Um, right? But that stored graph is the key to everything because it remembers every operation and input. It can later be walked in reverse to compute gradients. That's exactly what the next chapter are about, right? So let's go there. Um, so loss function, right? We have a prediction and a way to run the network, right? Now, how do we measure and then minimize how wrong the prediction is, right? So what is a loss function? So here's the problem. The forward pass gives us a prediction, but a prediction by itself doesn't tell us whether it's any good. To improve the network, we first need to measure how wrong it is. A single number can we can push down, right? So that number is the loss. A loss function takes the prediction and the true answer and returns one scalar. Zero means perfect, large means worse, and that gives training a crystal clear goal. Find the weights that make the average loss over all the data as small as possible. So you can see it here, the prediction and the true label, um, right, both feed into the loss, which outputs a single scalar, right? And different tasks need different losses, each paired with a matching output layer. Classification uses cross entropy, regression means mean squared error, and so on. Right? So let's dive deep into mean squared error and cross entropy. Almost everything reduces to two losses. And let's define both, right? Uh, Mean squared error for regression, when you are predicting a continuous number like a piece, like a price or a temperature, um, it simply penalizes the squared distance between the prediction and the target. Um, right? It's zero when they match, growing quickly as they drift apart. Cross entropy is for classification, right? The model outputs a probability of each class, and cross entropy rewards putting high probability on the true class. With one hot labels, it simplifies to just the negative log of the probability you assign to the correct answer. Now, the initial question is, for classification, couldn't we just use MSE on the probabilities, right? So it turns out that cross entropy trains dramatically better, and the next slide shows you why. So here's the reason, and it's all about the gradient. Cross entropy punishes confident wrong answers harshly. Look at the curve, right? So as the probability you assign to the true class drops down to zero, the loss shoots up to infinity, right? Um, so, but the decisive difference is what happens to the gradient when the model is very wrong, right? With the cross entropy, the gradient is about -1. A full strength correction signal with MSE, the gradient is close to zero because it gets multiplied by the flat part of the sigmoid, which kills it. So cross entropy delivers the strongest push exactly when the model is most strong, precisely when you read it, right? When you want it, right? So while MSE goes quite at the worst possible moment, that's why cross entropy is the default for classification. And here's a sanity check you will use constantly. In the note at the bottom, before training, an untrained K-class model spreads probability evenly. So your initial loss should be about the natural log of K for 10 classes, right? That's about 2.3. If your step zero loss is way higher, say 15, that's almost always a data bug, right? Um, One hot labels where integer indices were expected, misaligned data, or a double softmax, not your learning rate, right? So, right. So let's then go to the next chain rule in the propagation. Now, the heart of how network learns, right? So um, we've gone through how the forward propagation works, but how does the weight actually get updated, right? That's the part we'll cover in this chapter. Um, so how do we update the weights, right? The answer is always gradient descent, right? So the gradient descent of the loss with respect to the weight points in the direction that increases the loss fastest, right? So we step the opposite way downhill by the same amount, um, called the learning rate, right? Eta. So that is the update rule. W becomes W minus eta times the gradient, right? Um, so picture it as a rolling ball down the hill on the loss surface. Each step is one of these updates, and the ball rolls down towards the minimum, right? A low loss set of the weights. Uh, and here's the notation we will use for the rest of this chapter. So let's lock it in. X is the input, W and B are the weights and biases of the layer. Z is the pre-activation. Now W times previous activations plus B. A is the activation after applying sigma. Y hat is the final prediction. L is the loss, and eta is the learning rate, right? Um, so gradient descent needs the gradient of the loss with respect to every weight, right? So the naive way to compute that is nudge one weight, rerun the whole forward pass, See how the loss change. Repeat would take one full forward pass per weight, right? For a model with million of parameters, that's completely hopeless. So what we do, right? So we look at the back propagation as a solution. Using the chain rule from calculus, we can compute all the gradients in a single backward pass, sieve through the network. Total cost about the same as one forward pass. This efficiency is the reason why training deep networks, right, is possible at all. So here's the elegant part, right? Define each layer's error signal, um, delta L. Backprop is a recurrence, right? The error signal at layer L reuses the error signal from the layer L minus one, L plus one, sorry. The next layer passes its error back, and we just multiply by the local gradients, sigma prime. And once you have the layer's error signal, its weight gradient drop, so right out, right? It's just the error times the incoming activation. So the work is never repeated, right? The signal computed from the next layer feeds directly to the previous layer. One sweep from output to the input back, right, gives you every gradient. So let's watch it happen on a real network, right? The forward pass is already run, right, and computed every activation. Now the backward pass sweeps from right to left, right, and it started the loss um, with the error on the prediction, del L over del Y hat, right? That flows into the output layer. We compute its error signal del 3, right? Delta 3 and the highlighted edges. The weights from the weights from hidden layer 2 into the output are exactly the W3 weights that now get updated, right? The hidden 2 layer, we get delta 2 from delta 3 and the hidden 1 to hidden 2 edges. All right. So W2 gets updated here. The hidden 1 layer um, gets delta 1 from delta 2 and the input weights, right? W1 gets updated. The gradient flows backward, um, and each layer updates its weight as the wave reaches it, right? And in the code, the entire sweep is one line, right? Loss dot backward. It runs everything you just watched automatically. Each layer reuses the activation the forward pass stored, which by the way is why training takes roughly 3 times the memory of inference. You're holding weights, activation, and gradients all at once. Um, So when gradients vanish or explode, right, there's a catch with deep neural networks because backprop multiplies many factors together. The size of those factors matters enormously. If each factor is less than one, the product vanishes 0. Uh, you know, uh, 25 to 50th power is nearly like 10 to the power minus 30, right? Effectively zero. So the early layers gets no signal and stop learning. If a factor is greater than 1, the output explodes, the gradients overflow, the weights becomes LAN, and the training diverges. One fix for exploding gradient is gradient clipping, shown in the code, right? And the broader fixes are here, right? ReLU instead of sigmoid. Residual connections that give gradients at a highway, a good weight initialization, gradient clipping, and a normalization layers. So quick check, right? Suppose your first layer's gradient norm prints as 10 to the minus 18, right? Um, while the last layers is a healthy 0.45. What's going on, right? Can you think here? What is wrong here? Right. So, as you just saw, right, it's the classic case of vanishing gradient, right? So, right. So there you should use ReLU or GELU instead of sigmoid, right? Residual connections or normalization, right? So this is basically end of part two. Let's recap what we see here. We saw the forward propagation, how it pushes the signals from input to the different layers for prediction. There's a loss function, right, that corrects what is wrong in the current basically scores how wrong is the current prediction, right? And then we saw the backpropagation on how it updates the weight of the model to basically update basically and help it to help each of the weights in the layer update right in one single pass, right? So um, so in the final part, we'll go through some of the we'll turn these gradients into good training, the optimizer, the regularization, and the full training loop, right? And that make models actually work in practice. So like we just saw, right? The backpropagation give you gradients for each layer or each weight, right? But the optimizer is what actually um, decides what to do with that gradient, right? So we we saw plain gradient descent, right? Step downhill by learning rate times the gradient, right? It's called SGD, and it's simple but fragile, right? It struggles in few ways. In long narrow valleys called ravines, right? It bounces back and forth across the walls instead of moving along the floor, right? At saddle points where the gradients is near zero, it stalls. A single global learning rate can't suit parameters that need very different step sizes. At each mini batch gives only a noisy estimate of the true gradient. So the step shows some jittery patterns, right? So here's what we want the optimizer to add, a momentum, right? To smooth out the noise. Adaptive per parameter learning rates. Robustness, so we don't have to tune endlessly, and a tendency to find flat minima that generalize well. So the next few slides add these one at a time, right? So we see two upgrades, momentum and adaptive rates. The momentum fixes the direction. Instead of stepping on the raw noisy gradient, we keep a running velocity, a moving average of past gradients, and step along that, right? It's like the ball gaining speed. The back and forth zigzags cancel out while the consistent direction accumulates and accelerates. So you can see it in the plot. SGD oscillates, momentum smoothens, right? So the second idea is adaptive learning rates uh, from an optimizer called RMS prop, which fixes the step sizes, right? So it gives every parameter its own learning rate by dividing by the recent root mean square of the gradient, right? Uh, Parameters with consistently large gradients take small steps. Parameters with tiny gradients take larger ones, right? And that's the fix, right? And then we have Adam that combines both these ideas, which come on the next slide. So Adam is basically momentum and RMS from put together in one optimizer. It tracks two things. The first moment, M, right, is a smoothed average of the gradient. That's the momentum part, telling you which way to go, right? Um, the second moment V is the smoother average of the squared gradient. That's the RMS prop part, telling you how big a step to take. There's also a bias correction step because M and V both start at zero. They are biased towards zero early in the training, and dividing by 1 minus beta to the beta 1 um, at timestamp t corrects that, right? The net effect is fast, stable convergence and a very little tuning. This is exactly why Adam is the go-to default optimizer, right? Um, so there's one important refinement of Adam called Adam W. Weight decay is a technique that keeps weights small to prevent overfitting. The problem with classic Adam is that it folds the weight decay into a gradient, right? And then divides it by the adaptive term. So parameters with large gradients barely get regularized and others get over-regularized. AdamW fixes that by decoupling the decay. It applies it directly to the weights outside the adaptive step. So every parameter gets uniform regularization. This is the optimizer that trains virtually every large moment model today, right? GPT-4, Llama, BERT, Stable Diffusion. And you always pair it with learning rate schedule. a short warm up where the rate ramps up gently so early noisy gradients don't blow things, right? Followed by a cosine decay where smoothly anneals down so the model settles with a good minimum. Right. So let's move on to the next slide. Um, So here's a practical summary. Rather than, I'll give you a quick advice, right? Start with AdamW. Learning rate 3 to -4. Uh, Weight decay 0.1 plus warm up and cosine decay, right? That's the safe default for almost everything. If you're training a CNN and chasing maximum accuracy, switch to SGD with momentum for the final runs. Adam converges faster, but SGD with momentum often generalizes a little better on vision, right? And one thing to watch is in the note, right? Adam W is with no warm up will often spike to NAN in the first 100 steps because the bias correction amplifies those early noisy gradients. This is a short warm up fix that you can do. So now we'll talk about making the model work on data as I've never seen, not just memorize the training data, right? So the problem is overfitting. A model with enough capacity to can memorize the training set, right? Including its noise. So instead of learning patterns and generalize, the telltale sign is a big gap between training and validation accuracy. So 99.8% on training, but only 72 on validation. That model learned noise, not signal. So here are the four main tools to fight it. Dropout randomly zeroes out some activations during learning, during training. So no neuron can only over rely on any other, right? It forces redundancy. L2 and L1 penalties add a cost to the large weights. L2 strings them smoothly. L1 tries them many weights to zero. Early stopping watches the validation loss and stops training once it stops improving, right? Plus label smoothing and data augmentation help too. So you should apply these and apply these. And in our example, the gap closest to right the from 97.8% in training, 24% validation of much healthier, right? So um, let's move to batch normalization. So one more technique worth understanding is batch normalization. The problem it solves is called internal covariate shift. As the earlier layers update during training, the distribution of inputs to the layer keeps shifting, right? So every layer is chasing a moving target that makes training slow and unstable. What Bayestorm does is, for each feature, it subtracts the mini batch mean and divides by the standard deviation. So activations entering the next layer have a stable mean of 0 and variance by 1. 0 and variance of 1, right? Then it learns a scale gamma and a shift beta, so the network can recover any distribution it actually needs, meaning normalizing z costs no representational power. And how it helps basically is it stabilizes those distribution, lets you use much higher learning rates so training is faster, acts as a mild regularizer, and smooths the loss landscape. One thing to remember in the code is Batchnorm behaves differently in training versus evaluation. So you must switch the model to eval mode at test time. Right. So now let's assemble everything from the last six chapters into one single loop that every model follows, right? So here's the one training step, and it's the same six step that moves every time, right? Um, so So clear the old gradient is the first step. Forward pass to get the prediction. The second step, compute the loss, and then backward pass to get the gradients, right? The fourth step would be to clip the gradients to prevent explosions. And optimizer step, which updates the weights. Then you loop back and do it again for the next mini batch, right? Um, and once per epoch, after you have been through all the batches, you step the learning rate schedule, run validation, and check whether to early stop, right? Um, now Uh, right. So this is the whole six-step process. Now let's put whole thing into actual PyTorch, right? Which is around just 25 lines of code, right? So we should read it as four block. The first block basically have some linear transformation layers with bash term applied, ReLU applied, and dropouts applied, right? These are the best practices. Then you have the loss or and the optimizer component where you compute the loss, you pass that loss to the optimizer with some learning rate and wet decay. So block three, the inner loop, basically has six steps you just saw: zero gradients, zero the grades, forward, loss, uh, propagate the loss backward, clip, and then step up, right? The block four basically is the where you run the validation, right? To do early stopping, right? Honestly, almost every model you train this summer is a variation of this exact template, right? So you should follow these steps. Um, So let's just look into some of the bugs that you might hit while training your model, right? So these three account for a huge share of the why my model doesn't train problems, right? So bug one is you forget to call out the zero grade. So gradients accumulate across batches and your loss oscillates slightly. The fix is one line at the top of the loop. The bug two is you forget to switch to eval mode at test time. So dropout and bash norm stay active, and your validation accuracy jitters from run to run. The fix is to put model.eval, right? Third bug you might see is your learning rate is too high with no clipping. So the loss explodes to none within a few steps, right? The fix is saner learning rates plus gradient clipping. Learn to recognize these three symptoms and you will save yourself hours. Okay. Um, so next we look at how to fix a overfitting model, right? So here is a quick before and after that ties it together. On the left, a model with no regularization, 99.8% uh, training, 72% validation loss. A classic overfitting scenario. On the right, the same model with dropout, wet decay, and early stopping added. Validation jumps from 94%, jumps to 94%, right? Um, and a workflow trip, right? When you start a new model, first deliberately overfit a single batch to prove that the model can learn, right? Then only add regularization, watching the train validation gap shrink. Okay, so here are the key takeaways, right? So, an architecture, first of all, right? So, an MLP is staked linear layers with activation and depth makes it a universal approximator regarding training. So every model follows forward, loss, backward, update, these four steps at least. Activations may use ReLU and GELU for hidden layers, softmix for outputs, and never sigmoid deep in network, right? The loss, cross entropy for classification, MSE for regression, always pass raw logits to the and then cross entropy loss. Okay. Um, Optimization, AdamW plus warmup uh, plus cosine decay is the modern default. In generalization, dropout, weight decay, early stopping, and bash down. If you remember one thing from each of those boxes, you've got the foundation, right? And that's a complete picture, right? From a single neuron to a multi-layer network with activations through forward propagation, loss functions, and backpropagation to the optimizers, regularization, and the full training loop that makes the model work in practice, right? The one pattern to carry with you is forward loss, backward update, right? And repeat, right? Thanks so much for watching. I'll, and uh, leave any questions if you have in the chat. Thank you.